Now at the bottom of page 2 there's a series of graphs of different log functions. One of those you have seen before, this log base 10 of x, this one here, is this kind of blue one here. You'll notice that they all go through this point here, the point 1, 0. And that's because if you ask yourself, for example, what's log base 10 of 1, you have to ask 10 to the power of what gives me 1. And it's always 10 to the power of 0, or 5 to the power of 0 gives me 1. So whenever you have an x, an x value of 1, whenever x is equal to 1, your y value, right, the logarithm, is going to be equal to 0. And that's true for all logarithms. They all go through that point. And you'll notice also that this thing here is the vertical asymptote. It's what this line gets closer and closer to, this function gets closer and closer to the y-axis, x equals 0. Now, we can transform logarithmic functions, logarithmic graphs, in the same way that we transformed exponential graphs or polynomial graphs. If you want to graph negative log base 10 of x, that's negative f of x, if log base 10x is your original function. Now remember, log base 10 of x kind of looked like this. All that's happened here is that we've turned that function upside down. We've reflected it in the x-axis. Right? So we had log base 10 of x looking like that on the previous page. We've just reflected that over the x-axis so that it becomes this. In the second question here, this thing here, we've got log base 5 of minus x, and then we've got to add 2 to it. So first of all, imagine what log base 5 of x would look like. It would be somewhere over here. It would kind of look like that over here somewhere. Now, what's happened with the minus x, if you replace x with minus x, it reflects the function over the y-axis. So what was here has been reflected over the y-axis. And then this 2 here has the effect of shifting it up by 2 units. So there was a point which was, I think, the point 1, 0 that the original graphs all went through. What's happened is that point has been, so that would be the point somewhere over here. That point has been reflected over the y-axis to here, and then 2 has been added to it to move it up here. Then in part C is log base 2 of x minus 3. Whenever you have x replaced with x minus 3, it has the effect of shifting the graph 3 units to the right. So instead of the asymptote being here at x equals 0, the asymptote, the vertical asymptote, is at x equals 3 instead. Now we've just shifted the graph 3 units from where it was to where it now is. Now the last thing, and this is just a quick thing, is something called the natural logarithmic function. And you'll see that there's a button on your calculator which just says ln on it. I think it's the button just below the log button. So ln is a special function. It's not L times n, it's just ln. That's the name for it, the function. It stands for logarithm, it's the Latin for natural logarithm that it stands for. And it's the inverse of y equals e to the power of x. You remember from the previous section that there's a special number e, which is roughly 2.718, a special number in many ways. If you take the inverse of this function, you get x equals ln of y. Ln is really just the same as log base e of x. So it's no different from any other logarithm, it's just that it has e as its base. So instead of it being 10 to the power of x here, it's e to the power of x. Yeah, and so the same thing applies. Y equals e to the power of x, the inverse of that, y equals log base e of x, or ln of x is another way of writing it. And then it should come as no surprise that the same basic properties of natural logarithms apply. Ln of 1 is log base e of 1, so you think e to the power of what gives me 1? E to the power of 0. Okay, so these properties here are exactly the same properties as apply to all the other logarithms.